I think you should start, but Leo.
Yeah, okay. So welcome everyone to this session organized by the History of Economic Society on the computerization of economics. So we'll briefly introduce the special issue for which this is a session that was organized. And then we will start. Unfortunately, one of the participants that is advertised on the program cannot join us. That is Pierrick Deschaux. So we will have 3 papers during the session. So first, yeah, this session is part of the project. There is a special issue for the journal Economia on the use of computers, software, data sets, computer programs, but also information that are available on the internet in the history of economics. It's edited by Marcel Boumans, who is here and will be a discussant for the session, Pierrick Deschaux, who cannot be here, Francesco Sergi, and myself. And we will have 3 papers today, but there will be almost 10 to 15 papers in the special issue, and we hope you will read it when it will be ready. So we will start by a presentation by Chengtang Cheng from the National Taipei University. So the title is From Computers to Computers, and it's on the Cambridge tradition in microeconometrics. So I will just give you the floor right now. Just a small precision. We will have a discussion after each presentation, which will be 15 to 20 minutes. And after the 3 papers, we will have a general discussion on the commonalities between papers and more general question about the role of computerization. So Tang, if you want to share your screen and start, the floor is yours.
Okay, so can everyone see my screen? So I believe that the screen is shared. Okay, so thanks everyone. So this paper is about the computers at Cambridge in the United Kingdom. So the title is From Computers to Computers, and the ASSA was the computer, the digital computer used by Cambridge econometricians in the post-war period. And so this is basically a story in the United Kingdom and how these econometricians started to use computers to do their empirical work. Okay, so this is a brief outline, but this is a really big slide, so I'm not going to talk through all of the issues. So I just mentioned some of the important arguments of this paper and how I will proceed with my arguments, with what evidence. So the big picture, I think the participants is quite familiar with the story that has been written by Beatrice and Roger Backhouse. There is a paper on it's like an introduction of the use of computers in empirical economics, and so this is a general theme, and what I'm trying to do is to propose a case study, and it's a story of microeconometricians at Cambridge. And this is relevant to my PhD thesis, which was the history of post-war microeconometrics. So in this paper, I try to propose 2 questions. The first one is how the computer-based calculation reshape post-war econometrics, and how these computers change the research culture among econometricians. So to answer this question, I'm gonna use case study. And the case was I've repeated many times, it was the Cambridge econometricians. It was the institution called Department of Applied Economics. It was founded in 1946. And during the time, after 3 years, there was a digital computer called ASSA. It was electronic delay storage automatic calculators was put in operation. And so this was the time when econometricians, they try to, they have a new technology and they can use their data to solve their problems. And in this paper, I try to argue that the history of econometrics is best understood by starting with their contributions in the United Kingdom. And also, there was a new group dynamics between econometricians, programmers, data collectors, or assistants emerged. So I'm gonna elaborate some of the history during the time. So okay, so this is the introduction of the computer. So I'm gonna skip this slide. But the main idea here is, so it was so after World War II, there were many computers were built in many universities, and especially in the States and the United Kingdom. So the important thing is in the United Kingdom, there were 2 computers were built. The first one was called Manchester Baby. It was built in 1948. And the other one was the ASSA. It was built in 49. So during the time, these 2 institutions were competing, so sort of competitive relationship. And they were, so they have a goal is just to build a computer and to do and make the scientific work better, so they can produce more scientific work. And also, it was the time when Ragnar Frisch, he believed that the computer or the emergence of the new computational technique will revolutionize the field of econometrics. So how did it happen? So I pinned down this sort of story to Cambridge. So the Cambridge DAE, as I said, like it was Department of Applied Economics. It was new institution founded, and it was the idea was proposed by John Maynard Keynes before World War II, but the idea was delayed until the war ended. So after, so the new DAE, the Department of Applied Economics, was finally launched in 1946, and the director was Richard Stone. So he was a famous national accountant during the time, and Richard Stone he set up the aim for the new department. So he has 3 aims. The first one is just proceed his work in national accounting, and the second one was time series econometrics, and the third one was applied econometrics. He didn't say, but it was actually referred to microeconometrics. So after setting up the institution, he started to find like new faculty members. So he got Roy Geary, Gerald Tinner, Guy Olcott, Donald Cochrane, James Durbin, and Jeffrey Watson. So they were some of them are becoming famous for their contributions to econometrics. So under this setting, what Stone trying to do is, of course, to do more applied econometric work. So he needs some of the computers or those calculators. And okay, so I'll skip this slide. So he's basically introduced Stone. But Stone, he wasn't the central figure in the story, but like he was central in the department, but in terms of calculation, the central figure was Guy Olcott. So he got his PhD from the States. He came to Cambridge, and Guy Olcott was famous for his regression analyzer. So to briefly introduce regression analyzer, it was a machine invented by Olcott to perform the task of regression. And he brought his machine to Cambridge. So it was the first time Cambridge has this new machine to do the regression. So during the time, so when the DAE was founded in the first 4 years, they focused their main task on time series econometrics. So the main outcome was Cochrane-Olcott estimator and Durbin-Watson test, which were basic tools in time series econometrics. And also, but after that, Stone, he started he thought time series econometrics was enough, and he tried to shift his research focus to microeconometrics. So during the time, during these 3 years, there were no calculations were produced by digital computers, of course, because the ASSA was put in operation only in 49. So before that, they basically relies on human computers and also Guy-Oaker's machine. So it was the computers during basically looks like, right? So there were 2 quotes I use here. One was by James Durbin. He was saying that the DAE was actually so the computations was done actually by many young ladies. So these young ladies, they were computers. They sit in the room and working on the desk calculators. And also there's another quote was from Lucy Slater, and I will speak about this person afterwards. And she was saying that basically the same as Durbin. So it was a women room, and they were doing ordinary merchant calculators. So on the right hand side, there was it is the merchant calculators looks like. So basically, like it's like many desks, and every woman has a calculator, so they perform their calculations. And actually, okay, so this is one type of computations at Cambridge during the time. And another type was Guy-Oaker's regression analyzer. So the analyzer, Guy-Oaker's analyzer was a machine, basically a machine, but he also needs some women to do the card punching. So the idea of the machine was like, so they have a big machine here, but you punch the data into the cards, and they feed in the cards and do the calculations. But in order to complete these tasks, they also need women to do the card punching. So it's basically similar, right? So, but the machine. So, but if you feed this punch card into a machine, you just let the machine do the work, and this machine slightly increases efficiency of calculation. So so from the article, you can see the efficiency of this machine. You can accommodate up to 30 observations and handle a simple regression in 40-50 seconds. So well, it's a nice improvement, but it's not huge improvement. So this was basically the machine looks like. So I have a paper about Guy-Oaker's machine, but I'm not going to talk through the details. But it was basically looks like the just you see on the right hand side. So this is how you punch this card into the machines and do a regression. So, but afterwards, as I said, there was a new computer called ASSA emerged, and in 49, and it was also the time Richard Stone he tries to recruit some of the econometricians to do the new works. So there were 2. There were 2 important data sets was released, and it was a household budget surveys during the war, and which includes around 10,000 to 1,000 household observations. So these econometricians try to utilize this data. So and also they have the new facility. It's just a new digital large scale digital computer. And so during this period, there were 4 important econometricians came to the DAE. Was James Durbin and Henry Huntaker, Sigbert Preis, and Alan Brown and John Aitchison. But I'm not going to talk through all of them. But the important people were Huntaker, Preis, and Brown. Why did that? Why were they? I will talk through a little bit about this. So during these 6 years, econometricians produced three important monographs in econometrics. So one was Stone and Roy on demand analysis, and second one was Price and Huntaker on consumer behavior, and Brown and Altus on log normal distribution. So why Huntaker? So as I said, Huntaker, Price, and Brown were important figures during the time because they were programmers. So Huntaker was an economist, right? So he was famous for he got a Clark medalist afterwards, and he was famous for his theory of review preference. But he was an econometrician as well. So he stayed at the DAE for 3 years and came to the US afterwards. But during the time at the DAE, he served a really important role in developing those econometric programs. And also Sigmund Price was a student of Stone, and he co-authored with Huntaker with many articles and also an important book on the analysis of family budget. And the other one was Alan Brown. He has his experience with the Ministry of Food, and he came to the DAE and stayed. I think he ended up at Oxford. So he also has this idea of doing empirical analysis on food demand, but he was also the main academic programmer for the new ASSA. Okay, so these are 3 important contributions produced by these Cambridge econometricians, but I'm not going to talk through these contributions. But the idea was like they actually utilized those new household budget surveys and produce some regression estimates and also solve the problems in demand analysis. So these 3 contributions are extremely important in the history of microeconometrics. And why did they produce those estimates was due to the ASSA. So the ASSA was a digital machine which can operate the orders and a sequence of orders called programs. And it was developed by the Cambridge University Mathematical Laboratory under under a person, Maurice Wilkes. So he was leading this laboratory and also do just basically the computer lab of Cambridge. And the new features of this ASSA, as you can see in the picture, is like they have lots of storage, and they can run conditional orders, which means that they can do calculations until something happens. For instance, like for some of the errors has minimized to some extent, and they stop. So, which means like you can do iterations. And also, of course, you have the shortened time and increase in efficiency. And so econometricians during the time, they were interested in using these computers, especially Huntaker, Price, and Brown. So they became the first generations of the programmers for this huge giant computer. And it was recalled by Lucy Slater. So she was saying that the economists were among earliest users of this computer. And what did they do with these computers? So they were 7 main tasks. So basically just speed up the computation. So you can do a moment matrix or matrix inversion or some of other more complicated computations, and you can save more time. And also, this is another important feature was they started use this computer to do multi-causal simulation. So, so this is a quote about the efficiency of the ASSA. So after I think after 1 or 2 years, Brown, Huntucker, and Price, they figure out how to do computers, and they published an article on in the Journal of American Statistical Association, saying like how to do programs with ASSA. And they say it was so the new efficiency was 7 minutes to out 55 weighted sums of squares and other different things. But those, if you do those calculations in human computer, like these women computers, and they would spend a lot, like 75 hours to do this job. So it's a huge improvement on the efficiency. And they started to argue that those any research workers should be they would benefit from this huge saving of time. So the argument here is I think this is a transition from the human computers to digital computers, and also signals the econometric works are done differently. So why do I say that? Because like so there's a quote from Roy Allen, so who was a statistics professor from the ASSA, and he was saying this vast enterprise, saying like it became so like econometricians became teamworks. So before that, it was usually econometrician. He has an idea and he just runs some of the very small amount of observations. But after if you have this huge computer, you need a programmer, you need data collector, you need your students to do some of other works. And so this is a time when doing econometrics became differently. And so I think in this paper, I try to argue that new computers have changed the way how econometricians collaborated. And also programming expertise became extremely important in this story. And why do I say that? Because you need a programming expertise to economize the program, and also you need someone who knows computers, also knows something about econometrics, and he or she can do the work. So that the new image becomes like that. So econometricians, they, from the ideal side, econometricians, they have their idea, and also they consider a program, or programmers consider a program and write up routines and try to economize the program. At the other side, you need another work, someone to collect data and someone to punch the data. So in that sense, punching the data also needs women computers. So women computers didn't disappear during the time. They just shift. The work they have done just shift from doing desk calculators to car punching. So it doesn't make much difference for those human computers. So in that sense, the need for punch card typers still existed, but in that sense, there's a new demand for the programmer. So the programming expertise became extremely important. And there was a case it was a case about it was from Guy Oka actually, but it was actually Oka trying to do something, but he didn't have a programmer, so he failed. So there's a story I described in my another paper. So who was the programmer during the time? It became an important issue. So the programmer for the DAE was actually a woman, and her name was Lucy Slater. She was the main programmer for the DAE. After earlier, like after Huntucker Price, they left. So Alan Brown, he was he started to think that is important to like to need a professional programmer, because Alan Brown, he was busy for doing some other things and he doesn't have time to do a program. So DAE decided to hire a programmer, and the programmer was Lucy Sarah, and she had a background in mathematics and also has an experience working with ASSA for I think 3 years. So she was hired as a main programmer and just do the programming work. So like she became the mediator between the computer lab and the DAE. And so this is some of the evidence I found quite interesting, because this is the programming sheet in the Cambridge archive. So as you can see from in 1951, the programmer for the DAE was praised, and but after 1955, the programmer became Slater, and Slater she served as the main programmer for the DAE I think until 70s. So she was the main mediator for the department, and she has to ask every econometrician like what you want to do, and I will economize the program, and I will communicate with the computer lab. So this is an extremely important role, but it was never being emphasized for our history of economics. So these tasks, as you can see from 56, they have different projects, and also they have some of data on like how many times they have been used, and who were leading the project, like Stone or Brown, or just simply do the problem analysis. So, but it was all handled by this person. So that reinforced my argument about the new dynamics between econometricians, programmers, and also other people. And also, it perhaps like it is fair to argue like she was the hidden figure for this department. Okay, so to conclude, I'm not sure what time is it now, but to conclude, so the first quote was from Stone and Roy about in their monograph. So Stone, he started to realize to do econometric works needs different people, like different coordinations between different people. And there were mathematical problems, there were statistical problems, there were programming problems. And I think the case of DAE is a really typical, maybe it's a really representative case during the time when the new computer emerged, and how these different balances, like power balances or different ways of collaborations will also change. So I think, so in that sense, I think this paper will give us more understanding on the history of computing and also history of econometrics during the time, and also have further thoughts on the research culture or some of hidden figures. Like we need to rediscover these hidden figures in order to understand the history of econometrics better. Okay, so I think I'll stop here, and I'm looking forward to your comments or our discussions. Thanks.
Thank you very much for this fascinating work. So I will first ask the discussants if they want to say a few comments, remark, question, and then I will open to the floor. Please use the Q&A box that you have on the toolbar, and I will then go to the questions. So maybe Marcel, you want to start?
That is fine. I could start. Thank you, Tang, for your wonderful presentation. It raises all kinds of important issues. And it also makes that you start really to think about what does it mean, the practice of using computers in econometrics. It also raises some questions. That's a good thing about good research, that it raises questions more than answers. And I just, one of the questions that I had is that why did they start using computers? The way you present it is very much, okay, we have a calculating machine and that is faster. I'm not so sure whether this is the case, particularly when you say, well, what we need is at Cambridge, where one of your first slides you said what is needed is statistical realistic economics. So perhaps you could elaborate more what the aim was and what they expected from the computer to do for that purpose. If it is only a faster calculating machine, that's fine, but I have the impression that it seems to be more at stake. And actually, what I very much like about it is, of course, showing hidden figures. And this in the case of Lucy Slater. But I still have questions about her role, because the way this is still presented, if all the task, theoretical part, the programming part, the data analysis, the processing, the punch card, as if these are all very separated tasks. And I just wonder whether, so you introduce Lucy Slater as a programmer and as a mediator, but I wonder whether her influence is even more than that. Because on one of the slides, on one of the last slides, you show from the archives that she was involved with linear programming. Yes, development of linear regression programs. And I wonder that, because I have the idea that the techniques, the way the techniques were developed, were very much aligned with the development of computer programs itself. And I can imagine, but of course that is a question to you, whether you saw something that she has also influenced for what is needed for the computer, the method itself, so that she really became part of what we have separated from the programming, namely the development of econometric methods. Okay, that's my comments and my two questions.
Okay. Should I answer first or?
Yes.
Okay, so
I ask my question first because they are very much in line with what.
Yes.
So you can loop them together. So I too have a question on women in the history of computerization, and a question on the distinction between the computerization side, the mathematical side, and the econometric side. So with respect to women, what is interesting is that so there's already a lot on the history of women as operators, and here when the focus in Lucy's letters shift the emphasis from operators to programmers. And it's not so much apparent in your slide here, but in another version of the slides that you sent us, you say that one of your research questions basically, do the existence of this computerization change the cultures of econometrics? Mm-hmm. And so one sub-question in this is whether the fact that part of the computerization is done by women actually changed the culture of econometrics, and the response can be different. You could say, for instance, the fact that it's women that operates the machine doesn't, but the fact that, for instance, Lucy Slater did the programming does. Mm-hmm. In one locus where this plays out is that when you're, I don't remember which language it programs, but one question is how much background in mathematics and in econometrics you needed, because she would say stuff like, in my language, I cannot translate what you want in that kind of syntax, and so you have to find another algorithm. In a computation, I will make a difference between computation and computerization. computation is essentially mathematical pen and pencil activity. And computerization is related to the activity that involves hardware. And one question that ties in with what Marcia was saying is that whether she had to cross the computerization programming aspect to go in the computational discussion, thereby also contributing to the mathematical foundation and how you calculate this estimator or whatsoever. And my second question also ties in with this kind of distinction. I mean, do you have example, more specific example that allows to disentangle and study the interplay between mathematical limitation or affordance, econometric limitation and affordance, and computerization limitation and affordance? For instance, when you say these techniques were used to operate matrix inversion, regression, and Monte Carlo simulation, what exactly are you saying here? Are you saying they allowed it to be implemented, these techniques otherwise created to run faster or to run at all, or even something that they allow these techniques to actually be created? And if so, is it because of the affordance of this new machine or because of the limitation of this new machine that it will lead to develop these new techniques? So that would be interesting, I think, to select, for instance, the Monte Carlo method or the regression method and to see how these various layers played out. But thanks for the it's really great.
Thank you. I just will ask a question from the chat, and then maybe you could answer what the question or select from it. So there is a question from Peter Meyer, who say very interesting. Were the DAE people closely in touch with Leontiev and Kuznets in the US? So if you could,
yeah. Okay. So okay, I start with the QA. So I think Stone, he was close in touch with Kuznets because they both working on the national accounting statistics, and they have some interchange a lot, but maybe not Leontiev. So, but on the other side, I'm not sure. Actually, I'm not sure. But I have thought many communications between Stone and Kuznets. So also, okay, so start from the Marcel's question about why do they started using computers. But I think there was actually quite a supply driven. What I say supply here was related to data. So because I think it was the first time when DAE people they started to meet this huge large scale data set, and in order to solve these, they need more computers. They need more computing power naturally, and also I think it was also relevant to the task because Keynes was saying like statistical realistic. So what he was thinking, I'm not sure what he was thinking, what he had in mind, but Stone he therefore set up this task is about mainly run regressions and depends on data. So you can run time series you can handle time series data in a rather reasonable way without computers. But when it comes to a large scale data set, then that's the reason why they need computers. And so, and the second one was about Lucy's letter's influence. So I think it was quite important because as a programmer, so I think she mainly serves as a programmer. And what programmers do at the time was trying to understand what everyone needs. So if someone needs some of the computations and he has some of the data and he has this model, and how could they feed in the computer? And it was so Slater, she was mainly in charge of this task. So it's something like translate from the data and ideas into and bring these ideas and data to the laboratory, to a computer lab, saying, okay, so I need to sort of those kind of things. And she figure out and program a program and bring that to the computer lab and tell the computer stuff to do that. So this is what I understand. So, but maybe there's some details I have missed, but you know, because of the stage of this paper, I'm not very sure, like what's the actual things. So this is the image I have from I got from the archive and document. And also I think after a few years, she became the vice director, something like, it's quite an important position for the department. So which means that she certainly served quite important, like quite crucial task for the department. Okay, so the first Beatrice question about computers. Okay, so I think this is quite very interesting because I think when that computer was invented, they both used the same language, programming language. So they only learned one. But it was actually a distinction between the computation and computerization because I think in her autobiography, Lucy Slater was saying when she was hired and she asked the director to hire like 10 women computers. So which means like she as a programmer also needs these computers. And so in Slater's case, she was definitely on the programmer side, and also but there computers, like human computers and programmer, were all omitted in this history. So I'm not saying like Slater was more important than these human computers, but I was saying they were actually a division, and those human computers, they just serve different tasks. So they're just changing from running desk calculators into car punching, and it's all very burdensome tasks. So
can you just wrap up, please? Yeah.
Okay. So the last one was the Monte Carlo. Yeah. So the Monte Carlo simulation is a really good example because in Monte Carlo simulation you need random numbers, and also you need repeated programs. So like you run this experiment on one probability, and you had to repeat this procedure. So this is how the computer engage with these activities. But and also you also need a program for generating random numbers. So yeah, it's definitely a very good example for how those to explain how the technologies actually change the way they do econometrics. Okay, I'll stop here. Thank you.
Thank you very much. So we'll, if you can stop sharing your screen. Yeah, Laetitia can share hers. So the next speaker is Laetitia Lennon from Humboldt University of Berlin. She just finished her dissertation on the transatlantic history of business forecasting, which has been awarded a Humboldt Prize. And this is, I think, part of your PhD, but I'm not sure. So the floor is yours. And yeah.
Thanks a lot, Cleo. Yeah, so I've worked on the history of business forecasting, but this history and the implications of the computer hasn't been part and hasn't been covered by my dissertation. But of course, it came up during that time and during my research. So yeah, thanks a lot. So economists conceive most economic and business time series to consist of seasonal, trend, cyclical, and so-called irregular components. To determine the cyclical behavior of an economic time series, they usually adjust data for seasonality, the secular trend, and irregular movements. In the mid-1950s, the analysis of a 10-year monthly series required about 2,500 computations and 5,000 if checks for correctness were counted. This, explained observers, took a clerk about a week. The large time costs of time series decomposition caused significant delays in the availability of adjusted economic data. Figures were therefore often considered too late to be of value and service. This posed a particularly grave problem in business forecasting. Economists and business representatives deplored that they were forced to make forecasts without knowing whether their country or business had been getting better or worse between the moment captured in the data and the present. The advent of large-scale electronic computers in the early 1950s promised to solve this problem. For the first time, it became possible to process economic data within minutes. However, electronic computers brought about new problems of time. First, they required complex infrastructures, which involved time-consuming and tedious organizational processes. Second, until the development of the microprocessor, computer time was scarce. Both factors pushed business cycle researchers to aim for ever greater standardization in the use of electronic computers. While this did indeed allow for an unprecedented acceleration in data processing, it introduced new problems which ultimately called into question the very project of forecasting itself. Focusing on the case of the National Bureau of Economic Research, my paper investigates these problems and their implications for the project of business cycle research and forecasting. The researchers of the NBR, particularly Wesley Mitchell and Arthur Burns, are well known for having developed the leading indicator technique, which up to date constitutes one of the most popular forecasting tools used all over the world. After a brief introduction of the leading indicator technique developed at the NBR in the 1930s, that will be section 2, I explore how researchers of the Bureau used electronic computers in the 1950s and 1960s to process monthly time series for forecasting purposes. I investigate the time-consuming routines that the use of electronic computers involved in section 3, and argue that these time costs push standardization efforts at the NBR. And as I show in section 4, standardization introduced a new set of problems, which eventually prompted the researchers to cease their efforts to forecast economic fluctuations. I now very briefly introduce the leading indicator technique. Under the leadership of Wesley Mitchell, Director of Research at the NBR until 1945, a group of economists collected and analyzed an ever-growing body of time series from 1922 onward to unravel certain patterns from which they could induce a timeless model of business cycles. The work was driven by the ideal of mechanical objectivity, with its idea that phenomena or the data bearing witness to them could speak for themselves. Along these lines, the researcher's objective was to start not with any preconceived ideas or theories, but with carefully screened observations, that's a quote, whose analysis would crystallize the features and mechanics of business cycles almost automatically. This analysis, again, was to follow a set course that would warrant the objectivity of the results. Mitchell's collaborator, Arthur Burns, once described their time series analysis as an apparatus that quasi-mechanically yielded certain results. The apparatus was a complex one. Over 1,000 time series covering a variety of economic processes in 4 countries from the 19th century onward were compared to so-called reference cycles intended to reflect the cycles in general business. These measures were made for the different cycles covered by a series and then averaged for each set of cycles. By this means, the researchers wanted to diminish the influence of random factors. Although aware, that each specific business cycle is an individual differing in countless ways from every other, the researchers nevertheless believe that their analysis would disclose, I quote, faithfully what cyclical behavior is typical of the process represented. When Secretary of the Treasury, Henry Morgenthau, asked the researchers of the Bureau in 1937, I quote, to set up for me the signposts to look for as we go down a depression, and also for the things to look for as we go up, the researchers agreed. In 1937, Mitchell and his colleagues presented a set of series that had commonly led the turning points of the reference cycle. As clouds precede a storm, that's a quote, and could thus be used as indicators or barometers of business conditions. In 1953, Arthur Burns, Mitchell's collaborator and successor as the Bureau's Director of Research, became chairman of Eisenhower's Council of Economic Advisors. As economic watchman for the White House, Burns had the chance to demonstrate the practical value of the leading indicators and to significantly enhance their prominence. With Arthur Burns and his colleagues of the Council regularly using and publicly commenting on the latest movements of the indicators, the system became known throughout the country, with simple graphs displaying the behavior of the composite indicators to the common reader. In the observation and analysis of the indicators, Burns closely cooperated with his colleagues from the NBR. From summer 1953 onward, Geoffrey Moore and other colleagues gathered, analyzed, and interpreted current economic data in an ever-increasing pace. The problem of forecasting became of foremost importance, fundamentally shaping the research agenda of the NBR. The researchers were electrified. As Moore put it in 1955, they hoped to have discovered, I quote, certain basic economic facts of life, which, while not necessarily impervious to change, might nevertheless prove to be lasting. Burns repeatedly asked his colleagues to speed up the time series analysis to be as up-to-date as can be, as economic events move so swiftly that indicators run quickly out of date. The reduction of the blind interval between the moment captured in the data and the moment the data could be funneled up to Burns by his staff therefore became of foremost importance. It thus came at no surprise that the advent of large-scale electronic computers in the early 1950s was applauded enthusiastically by the researchers of the NBR. The researchers were amazed by the extraordinary speed of computers, heralding that this would significantly improve both diagnosis and forecasts of business conditions. The optimism that electronic computers would solve the problem of time and business forecasting, however, soon became clouded by the fact that their utilization necessitated time-consuming tasks. In the 1950s, computers were still scarce. Researchers had to obtain so-called programming time or machine time on computers in different locations. Most of them were located outside metropolitan areas, thus necessitating long-distance travel. As the researchers had to shift from one location to another, they also had to work with different computers. For each kind of computer system in use, the researchers had to adjust their programs based on the system's specifications. To make matters worse, the computers they developed their programs for quickly became obsolete, forcing the researchers to continuously develop program adjustments. September 1966 saw the installation of the first large-scale electronic computer at the NBR. This saved much time as researchers no longer needed to switch between different locations and computer systems. But even then, machine time was scarce. And this is one of numerous memoranda circulated in the 1960s, asking the researchers of the NBR to help reduce time at the computer and between runs. Users were asked to submit their runs, particularly long ones, to be run after hours by machine operators. This involved being more careful in the preparation of control cards and developing more standardized procedures. So even after the installation of the first electronic computer at the NBR, the need to reduce machine time remained of utmost importance and deeply affected research practices. Thanks to electronic computer programs, which the researchers celebrated for providing for all these adjustments systematically and extremely rapidly, monthly series could for the first time be corrected and adjusted within minutes. Observation could thus be turned into indicators at lightning speed, the researchers explained. And the process became increasingly quicker. For the first time, researchers could increase the granularity of their analysis and analyze monthly series. Researchers celebrated this, declaring that these changes would allow for new degrees of forecasting accuracy. This hope, however, turned out to be in vain. As soon became clear, the computer was unable to separate meaningful signals from random noise in the current data. In their search for patterns matching their preconceived ideas of the business cycle, the researchers had until then relied heavily on judgment to retrospectively correct economic data for those components that did not fit what they had identified to represent cyclical movements. Based on the analysis of past data, they had carved out average cyclical patterns for every time series against which they had matched and corrected current data. Such exercise of retrospective judgment was obviously impossible for an electronic computer. The computer could detect neither unrepresentative periods nor highly extreme individual items, such as arise from strikes, as the researchers had not found any formula or automatic technique that would allow the computer to delineate the underlying cyclical movements. This, however, was made all the more necessary by the recent increase in granularity which the computer had brought about. As it turned out, the irregular factor was unproportionately large in the newly available monthly series. As a result, most month-to-month movements of seasonally adjusted economic series were not cyclically significant. As the researchers noted, somewhat disillusioned, the indicators were continuously fluctuating. From the formation of the NBR in 1919 onward, Wesley Mitchell and his colleagues had promoted the ideal of mechanical objectivity. Again and again, Mitchell had claimed that the Bureau's task was, I quote, to raise the discussion of public questions to a higher level by providing the public with objective knowledge of fact and not subjective impressions. The use of electronic computers in business cycle analysis showed, however, that the statistical methods developed by the researchers of the NBR to forecast business conditions were useless if not complemented by judgment. Business fluctuations, it turned out, became recognizable only retrospectively and through the use of idealizing intervention. Only human judgment had been able to tease out the actual patterns of the business cycle from the data. This was not only incompatible with the researchers' ethos of mechanical objectivity, it also cast doubt in the project of relying on past data to forecast the future more general. As the use of computers showed, economic data in themselves provided no useful knowledge about the future. An unforeseen recession put the final nail in the coffin. When the leading indicators failed to forecast the 1960 recession, the researchers began to issue warnings to not overestimate the forecasting power of their indicators. Geoffrey Moore explained that the indicators merely help to recognize business fluctuations at about the time they occur, or even after a peak of trough had been reached. I quote, "The business forecaster operates in a continuum, and the evidence for or against the judgments he must make from time to time accumulates months after month." As a consequence of their new cautious stance, the researchers ceased their efforts to forecast economic fluctuations. Instead, they confined themselves to keeping their indicators up to date for the benefit of other business analysts. In 1961, the National Bureau became the government's accepted judge of US recessions, announcing peaks and troughs in economic activity for the Commerce Department, which published the turning point dates in Commerce Department publications. In their role as arbiter of the business cycles, the researchers did not attempt to forecast economic fluctuations anymore, but instead announced a peak in economic activity and the onset of a recession well after they had begun or even after they had ended. As Robert Hall, chairman of the Bureau's Business Cycle Dating Committee, explained in 1979, by the time we make our announcements, much of our audience may have lost interest in the subject, but making news is not our primary purpose. Although valid for 1979, this had not always been the case. In the 1930s, shortly before publishing the first report on the indicator technique, Mitchell had explained that the hope to find a way to forecast and control business fluctuations was, I quote, "what really justifies all the time I have put in on this job." The computer, however, had turned the researchers' attention away from the future and towards the past, and thus fundamentally changed their focus. Thanks a lot.
Thank you very much. This was well on time. So should we go for a round of questions from the discussants and then take question from the floor? So we could start again by Marcel. And
yes, thank you, Letitia, for your wonderful paper. Actually, there's one more general issue I would like to address, which I find very interesting for this case. You, in the paper, you make a clear reference, and also in your talk, to the ideal of objectivity. And I just wonder, so clearly for Mitchell, that was really something that was very important. It was a very important, as Destin would call it, an epistemic virtue. But there were also other ones, and I just wonder how that happened to be. So it started as an indicator, and Mitchell was even very strong on this, that he said, well, it's not about it. It's not, shouldn't ever be a forecasting machine. It should really tell you something about what's currently going on. At some point, and I didn't get how that happened in your paper, it turned into a prediction. And actually this turn into prediction actually worked against him. That is what your story is about, because the aim for objectivity got lost due to this fact. But it's very important, this transition to prediction actually harmed his own original program. So why did he ever go with this new change of focus if that never was his original idea? And he was right about it. But this also has to do with another issue about with the moving average, to get some hold on the noise. It also harmed another thing that it seems to be important: precision, because you couldn't see anymore when the turning points would happen within a year or 2 years or within a month or whatever. So it also, so this aim or this change, perhaps it was Burns that pressured him to do so, made that it actually worked against his program. So can you say elaborate a little bit more why Mitchell accepted the change of focus? That's my only question.
Thanks a lot. Should I answer right now? Okay. Yeah. So thanks, Marcel, for this question. It's a great question, and it gives me the opportunity to say something about actually an entire decade or even 15 years that that I did indeed not talk about in my paper. So things are, as always, a bit more complicated. So Wesley Mitchell was very determined on and very cautious in presenting these indicators and in stressing that what you just cited, that they are not a forecasting machine, that they always require an expert observer who looks at the specific conditions and yeah, well, supplements these indicators by judgment. And during the 1930s, and even after Henry Morgenthau had asked them to come up with these indicators, they were sometimes criticized for this, for their own stance in, or for their own way of being so careful of not offering expert advice, because this is what they did. And this is also something that I'm not talking about in my paper. So Henry Morgenthau asked the researchers to come up with these signposts, and the researchers did, but they didn't want to do the interpretation for Henry Morgenthau, and Henry Morgenthau was very disappointed about that, because he had hoped for definite knowledge, which the researchers did not want to give him. in the 1930s, so they continued with this stance, and then even in the early 1940s, even after the onset of the Second World War, Mitchell continued to stress that, well, we have to continue our research like the way we always did and be very objective and not rush with any seemingly definite knowledge that will then turn out or might turn out to have been wrong. In the archives, I found a lot of evidence apart from what is well known about debates in that time, a lot of evidence on how much the researchers were criticized for this stance, how much Mitchell was criticized for that in the 1940s, also from people at the administration and so on. But he kept to this stance, and things changed only after Burns became his successor. And Burns was really different in that respect. And all the more different after Mitchell's death, I think. And so he was the one to push this forecasting technique, and that was also, of course, then a result of him having become the chairman of Eisenhower's Council of Economic Advisors. So then, really, in 1953, when he became the chairman, that became such an important project, forecasting, but remained so only for 7 years, as I show in my paper. Yeah.
Thank you. Beatrice, do you want to ask a question, comment?
Yes, I have. I like the paper a lot. I think there's 3 stories in the paper, which I'm not suggesting you should write 3 papers, right? But I have a comment on each of them. I think there is a computer story. I think there is a big data story. And I think there is a politics and culture forecasting story. So the computer story is, yeah, it's a bit like the kind of question I asked Heng. I mean, it's encapsulated in one sentence you have in the paper, which is actually a quote, in that you repeat it somehow in your presentation. At some point you write, as soon became clear, the computer was unable to separate meaningful signals from random noise in the current data. And so I find that this is one of the key of the collective projects of understanding, is actually these people all saying the computer does this or the computer cannot do this. And a computer scientist will tell you, the computer does whatever you ask it to do. So it's the economists who don't have the right techniques to feed into the computer to actually disentangle the signal from noise, and basically you could program the computer to ignore some outliers or to ignore non-significant cycles, whatever, right? And so the question becomes, I also think the response that is basically introducing moving average is super interesting, because again, moving average is not a computerization stuff. It's actually pen and pencil mathematization technique. And so my question is, if really it can prove, so it could have been introduced for other purpose. If really you're arguing that it was introduced in response to the problem created by the computerization of forecast in that period, this makes total sense, and this is a pretty strong and interesting conclusion. Because again, it could have been different. Again, moving average is not something that there's not a computerization aspect in itself, but it can be developed in response to a computerization limitation, and that's super interesting. The big data episode, I know that lots of people consider that big data is something specific to the end of the 20th century, but lots of historians of science basically say you have a big data episode if you have a gap between the amount of data you're supposed to handle and the techniques you have at hand to handle these techniques. And so my question is, do you think you have a big data episode there? To me, it was reminiscent of what some historians of science have written about the 1880 census, in which they had so much data that they could not tabulate it anymore. So they organized a contest for people to offer better techniques and better machine to compute them. And this gave rise to the use in the development of the Hermann Hollerith machine. And so maybe that's a way to frame it here. I don't know. So my question is, do you think there is a sort of like big data or data gap, gate data technique gap episode is it the story you're telling here? And my last comment is about that culture and politics of forecasting, and this also focus on that judgmental versus mechanical forecast. This is something that I find, so I work on the history of central banking, and these very terms, mechanical forecast versus judgmental forecast, I find everywhere. It's all over the place in the at the Fed in the 60s when they developed the MPS model and their extensions. And in the chairman, Martin, who comes from a banking background, basically says, okay, that's mechanical forecast. It's not that useful because, you know, you need a feel for the market. And if you do this kind of like large-scale macroeconometric model, you lose that feel for the market. And what is interesting is that at some point, Burns shows up as the chair of the Fed, and you would imagine that this sort of improved the fate of macroeconometric forecasting, and it doesn't. And the reason it doesn't is because he very well understands that the forecasting at the Fed has a political implication, and it wants to keep the ability to choose the most politically influential and acceptable scenario. And the forecaster at the Fed have a whole stories about making scenarios in a way that Burns would choose the middle scenario to make it appear like a sort of middle whatever. And you also find this judgmental versus mechanical forecasting debate at the Bank of England in the 90s. So I guess it's permanent in the history of forecasting. And because of how Burns shows up and the political implication of how you can do forecast and what happens if you what you lose if you mechanize the forecast is fairly interesting. And it was just a comment that the political aspect of this does not show up in your own story. And I wonder whether you had some evidence of this.
I'm going to read a question from the chat, and then if you can answer whatever you want from all those very interesting questions. So it's a question from Bud Collier. The Harvard Economic Service crashed and burned with bad forecast for its forecast on the eve of the Great Depression. Why do you think the NBER are so, it would be better with their leading, it would do better, sorry, with their leading indicators?
Okay, thanks a lot. So I'll start with your last question, Beatrice. So that is really interesting, and I'd love to hear more about it. It sounded a bit as if you had records on Burns talking about that and on his decision to not go with the mechanical forecast. So that sounds really super interesting.
We've used oral histories not from Burns, because he would not say I'm doing a political decision, but we have interviews from it's online, and we'll send the links to you, from former forecaster that were not really happy with what Burns was doing regarding forecasting at the Fed. Yeah,
that's so interesting. So in my history on business forecasting, I have the impression that this idea that the forecast itself influences expectations, and by this means the economy, and is thus a highly influential and political endeavor, that this idea really only comes up in the 1950s and as a result of the forecasting experience and the result of the research again on forecasts and on expectations. I leave it with that. And so also these leading indicators, when it became clear to the public that the administration under Eisenhower heavily relied on these leading indicators, the leading indicators suddenly became very, very popular. And I found a lot of evidence that business analysts and journalists and many agents began to consult these indicators only because they knew that the administration was relying on them, and that is what made them important. So not that the indicators may have been reliable or not, but that the administration thought them reliable and used them. So that happened in that time and during the 1950s. And so yeah, I would say, yes, it becomes a very political story. It has been before, of course, as well, but the consciousness for that is something that develops during that time. And also as a result to this new prominence of one forecasting tool of the leading indicators. About the second question, so I haven't talked about that in my talk now, but I've talked about the big data story in the paper that Beatrice and also Marcel were referring to now. I'm not so sure if I would say that it might be an episode on that more general, but I love to talk about it with you at one point. But in my paper, I made the claim that this expectation that the computer would allow economists to challenge economic theory and imagination and find new ways which were so mechanical that that it would really change the way research was done and even economic theory in the end, that those ideas which I found in the records of the 1950s, that nowadays, so contemporary expectations that big data has inspired parallel these hopes. And so in this paper, I was thinking about how this is also a narrative that has important implications, because it, as in the case of the NBR, because it in the end led the researchers to outsource their indicators or to not use them themselves to forecast, because they had so much hope that this would, the computer would allow them to really do a mechanical way of forecasting, that they then decided, when it turned out that it didn't, then it decided to not forecast at all. So I was rather talking about those hopes that for me are somewhat similar. Sorry about your first question. What was the first question? Could you say that again? Oh yeah, the computer story. Yeah.
Yeah, whether the moving average was introduced as a response. For computerization failure. But we can go for later.
Yeah. So I just very quickly. I would say it is because it was also a response to the newly available monthly time series, which was really a result of the computer. So this is just one reason why I would say yes, it was a result of that. And I might stress that more. And then about the questions from the chat. So so the NBR, so the Harvard Economic Service was a commercial service, and they got their money for the forecasts they made, and the NBR was just right from the start. They were much more careful, and they wanted they strove for a different reputation, and that was why they were so cautious. You asked if why I think the NBR thought it would do better with their leading indicators. I think so Mitchell was also thinking and commenting a lot on the Harvard Economic Service and their forecasts, and he was very impressed by their work at first, but then he had the impression that they were too hastily making forecasts without knowing enough about the past, and also not mechanically. And so why would they thought that they would do better? I think they just felt, well, we in contrast to the Harvard Economic Service, which published their first forecasts a few months after their after the formation of the group, the researchers of the NBR really waited with that, and they waited for 20 years and 30 years, and I think that was the difference. They had so much more data, and yeah, so that was what made them more confident to use them in the 1950s. And yeah, of course, they did have much more data and decades of work. Yeah.
Thank you very much. So we now go to the presentation by Andre on A Tale of Two Laboratories.
Thank you so much for having me. Let me try to share the screen, and I hope my connection will not disappoint. Excellent. So today I'd like to talk about the 1980s, late 1980s, early 1990s, and its importance in terms of computer technology on the emergence of the experimental economics laboratories and the impact of this technology. And this is a sort of a very typical graph you've seen from my other presentations about the growth of the experimental economics laboratories in that period, which hides, I believe, 3 stories at least, and they become more visible once they switch to a more logarithmic scale. And the 1980s, here you can see, is the sharpest or fastest growth in the number of active experimental economics laboratories, which is sort of the subject of my today's presentation and the paper that the participants and discussants have received. There is another story in the earlier period, from the mid-60s until the mid-1980s, where the question becomes, or is, what is an experimental economics lab actually? It's not about emergence of it per se, instead of the growth. And both together from the 60s until the 1990s present a third story about like what actually drives, what's behind the growth of experimental economics labs. So the first story in the first period was not just about what is the meaning of an experimental economics lab, and there were various attempts. Like, for instance, you had animals inside of the laboratory facilities, which were used to study microeconomic phenomena. You had, with pigeons and rats, but you had also attempts to make first computerized lab. But it was in general a question and a story about transitioning from classrooms to more classroom as ad hoc places to more dedicated places, which eventually became equipped with computers. The story is the question that I'm interested in today deals not just with the rapid growth of the labs in the late 1980s, but with the technological side, what actually allows experimentalists to take up computers in their experimental research. And all these things tie together in the question what drives the establishment and actual adoption. And laboratory experiments, and especially computers in their usage, are sort of a driving force behind that. So let me focus on the 1980s and early 1990s, and the backdrop of those events is the general decrease of the cost of computer technology, and sort of the general trend of exponential increases in computer processing power and transistor density, and also developments of various networking technologies, like local ones and more global ones, that fueled into the general adoption of computers, especially at universities. But this technological backdrop does not explain why computers became adopted by experimental economists as sort of the key element of an experimental economics lab. And so in this presentation, I'm exploring what's behind just this technological basic development, and that gets illustrated by two competing technological approaches of that period. There was the mainframe approach and the local area or LAN network approach, which were highlighted by two groups, one in Arizona, one at Caltech in Pasadena, led the first one by Vernon Smith, the other by Charles Plott, and had implications, the competing technological approaches had implications both on the hardware level and on the software level. When in 1975, Vernon Smith moved to Arizona, he soon discovered through a student of his that the University of Arizona library contains a number of terminals that were connected to a remote mainframe at the University of Illinois in Urbana-Champaign. And from the 1960s, the computer-based education research laboratory, CERL, and Minnesota's Control Data Corporation, CDC, developed the so-called programmed logic for automated teaching operations, shorthand Plato, which was the first computer-assisted instructional system for programmed learning, and which was adopted by a number of universities in the United States, and all the computations were done by the mainframe in Illinois. And what the users had at the local universities were sort of dumb terminals with keyboards and very fancy terminals which could be which had touch screens. It's very fascinating to imagine that in the 1970s you had touch screens which sort of fell out of use and re-emerged a couple of decades later. And so what Vernon Smith realized is perhaps this can be used not just for instructions but also for conducting experiments. There were some attempts to use computers in experimental research in the 1960s, which is sort of an important episode of Austin Hoggett's attempts to build a computerized laboratory, which disastrously failed. And so Smith used this available Plato system at Arizona to create eventually the Economic Science Laboratory. From 1975 until 1984, he used the library facilities with these terminals, but he had regular use of them, but not exclusive use. And anytime they were running experiments, the classroom in the lab, in the library, had to be physically adjusted for the purposes of an experiment. They had to place partitions between various terminals. For instance, they were programming their own classes, that is, they were programming their experiments. But by the mid-1980s, when they established the Economic Science Lab, driven by the tremendous success of the experimental research of the Smith Group in Arizona and publications in top journals, and also availability of funding from the National Science Foundation, they opened a dedicated computerized lab, the ESL, Economic Science Lab, which had 24 terminals in a dedicated room in the economics building. It had an additional room with a glass window where the experimenters were sitting, where you had printers, desks, and there was a special room for storing other equipment like bingo cages and other things that helped to run the experiments. And they had a separated sort of an entry room where the subjects were congregating before experiments. And this was all terminals that were equipped with Plato system. And eventually, and I will explain why, by the mid-1990s, they abandoned this technology and switched to other technology with locally networked computers. The issues that they were dealing with while using the Plato system was various technical issues in how to run experiments, especially message processing conflicts. For instance, whenever there was a thunderstorm in the Midwest between Arizona and Illinois, it caused sometimes disruptions in the connections because the terminals were connected via telephone lines. Eventually, they bought a dedicated telephone line to eliminate those errors, but it was, of course, expensive. And sometimes the people in Illinois were taking down the mainframe for unannounced periods of time to improve some issues or to deal with some issues that were outside the control of the experimenters in Arizona. The Plato system used so-called tutor programming language, which was used especially for developing courses, but it was very intuitive, and people in interviews keep telling me how easy it was to use. And they had to adjust it for various experimental economics purposes. For instance, it was very important that subjects see the same things at the same time, and with sort of a linear processing from the mainframe, they had to create various technological systems and also programming ways how to make sure that subjects see the same thing at the same time, and that speed is not necessarily the speed of a subject in typing things is not necessarily an advantage. By 1987-88, they switched to an upgraded Plato system, which didn't use telephone lines, but they switched to satellite communication, which is more fancy and allowed signaling through satellites. And eventually you use both local area network and also Plato. And the reason for sort of using this technology, which was actually very, very expensive to use, dedicated telephone line was expensive. Renting the time of the mainframe in Illinois was expensive, was that over the decade, they spent over 3,000 hours in developing software applications to increase their speed of their operations. And they were sort of locked in this technology that they were also promoting, but other labs were not. Some of the labs around in the United States used Plato as well, and they shared this technology, but it was prohibitively expensive for others to pick it up. On the other hand, in the 1980s, Charles Plott at the California Institute of Technology decided to use a different approach, to use computers, IBM Computer Model 50 in particular, that you can see on the slide. They used from 86 when the Experimental and Political Science Lab was opened, and what he used was a different type of technology of connecting the computers locally without the need for a mainframe somewhere else. Everything was located in the suite of rooms that were part of the lab that you can see here. It's still the original design, except for the computers, of course, have changed to use newer version ones. The lab consists of 3 rooms, one for conducting experiments that you see. There was a special room for coding and programming, and one for storage of data and experimental sheets and instructions and various secondary issues or documents that they kept for storing. The computers were sitting on rolling tables with movable transitions, all sort of having an importance and role for guaranteeing various aspects of an experiment, so that people do not see to their neighbors what they're doing, but also allowing the experimenters to see what the subjects are doing. The color scheme was chosen to make it a more inviting environment. The 2 plans are there for the same purpose, and all the PCs were connected by Ethernet. And like Smith developed a number of software packages, Plott developed the same thing. For instance, the Muda, which was distributed widely for multiple unit double auctions and other types of software packages. Eventually, especially from the late 80s through the 90s, the cost of computer technology, especially PCs, fell dramatically. And with the available software packages, both from Arizona, but especially from Caltech, allowed other experimentalists who didn't have the budgets for hiring programmers to program these types of packages, didn't have enough money, or they just had enough money to use available computer rooms in various departments, or buy computers to set up their own labs, tilted the advantage towards locally networked computers. With Muda, especially, eliminated Plato's advantage to run multiple markets, which is a very trendy thing to do in the late 80s, early 1990s. And you had other software packages for subject training, data viewing, organization of experiments, sharing procedures, graphics, etc., which not just lower the barriers of entry to experimental economics for other experimenters who just could use ready-to-wear, ready-to-use software packages, but also offered a greater experimental control in comparison to using just paper and pencil experiments, which is sort of the type of experiments you would do if you didn't have access to computer technology. And computerized experiments allowed better experimental control, which was sort of the thing that an experimentalist you're interested in. The hallmark of experiments is exerting experimental control and intervening in a specifically designed situation. And running experiments by pen and paper and people around is a bit different than when you run them via computers. First of all, you have far better control of subjects or subject pool. It's easier to record who participated in which experiments. There are fewer transcription errors than with handwriting. Also, the instruction delivery via computer screens is more allows real-time instructions instead of that people read and printed sheet. The instruction delivery can be split into phases, and each phase can be edited with some control questions for understanding, allows more individual pacing, etc. Also, eventually, once the computer subject pools became much larger and organized for databases, it allowed far better randomization of people who were coming to experiments, but also those who were already attending an experiment. They could be randomized into various groups that would be invisible to the subjects instead of when an experimenter is running around and randomizing on the go. Also, the uniformity of experimental conditions across experiments were very important. That allowed that you were the data collected was more reliable across experimental sessions. Furthermore, with computers, recording was far easier. It was easier to deal with various issues like changed number of subjects who showed up. It could be easily adjusted as a parameter in the experimental code. Instead of when you printed out, when you were expecting 12 subjects and suddenly you had 10, it's easy to switch than when you're fixed on 12 subjects. Of course, speed were an issue, and including real-time data analysis. You could see whether the market is converging instead of just painstakingly calculating averages, etc. And also feedback became possible through screens. That was different from verbal feedback. The feedback could be directed to a single person or people in a randomizedly selected group, or could be sent to everyone at the same time. It required also that experimenters had to learn how to program, either themselves or they hired specialized people, programmers, or as became more the norm, the graduate students learned how to program. From the older generation, not all the experimentalists program. From the younger generation, was mid-level career, mostly everyone had at some point had to program. But there was all sort of an operational level, the benefits of using computer technology, but on a conceptual level, there was a tremendous transition of what people could do with experiments. It was not just speed, but also what could be controlled and what could be designed in a laboratory computerized setting. Completely new types of interactions and institutions Like if you wanted to do say in not a first prize or second prize auction, but you develop a third prize auction that no one really thought about, but or no one really thought about of doing experiments because of complexity of computations. Suddenly you could do it easily in a computerized experiment. Also, you could start devising say multiple unit auctions, which were very hard to calculate in real time if you rely just on paper and pen experiments. And many such experimental settings eventually left the confines of the lab that were used for applied research purposes like spectrum auctions. And this deep interaction or deep connection to computers led eventually experimentalists to become inextricably linked to spatial arrangements, like where the computers are located, how they are separated from the others, how to control communication between subjects, how is the flow of information between among the subjects and between the subjects and the experimenter, how to perform randomization. All these things became linked to the special arrangements of the computers and the subjects in relation to each other and in relation to the experimentalists. So the experimental lab was not just a location with computers and then experimentalists and some subjects. It became a special space which had various epistemic functions and with a host of social infrastructure and division of labor of people with specialized rules and specialized tasks. And all the experimental labs, through and thanks to the computers, became focal points of experimental communities. That was sort of what the computerized technology allowed to do. So what I argued in the paper is that there are two ways how computer technology played a role in advancing and proliferation of experimental laboratories, the key period for sort of the experimental economics research or experimental economics in its whole entire history. And that is the computers were locked in a sort of two competing ways of how to do experiments, one using mainframes, the other with local network computers. Eventually, local network computers won because of the decreasing costs of the computers themselves, but also a host of easily portable software solutions that other people who were just entering experimental economics research could readily pick up and use for their own purposes. And on the other hand, computerized experiments provide many epistemic advantages over pen and paper experiments, and were closely connected to the control in experimental research. And here I'd like to stop and look forward to questions and comments.
Thank you very much for your presentation. I suggest we took the question from the discussant and you answered to both, and then we took the question from the floor. So Marcel, you want to start again?
Yeah. Yeah, I have just one, also due to the time we still left over for further discussion. I have just one question. You talk about the advantages, but part of your story is very much also about the disadvantages, all the technology, all the problems they have. If it would be only a story of advantages, I can see that it would be an explanation of the enormous increase of labs around the world. But considering the disadvantages, I don't see why it could explain that kind of enormous increase or that more increased in the 1980s. It doesn't seem to connect. So well, it was quite a move for economists who worked with pen and papers to move to really working with instruments. They have never done that before. And so they must be persuaded by something, but if they would know all the problems that probably they would soon find out, it doesn't explain the story. So that is what actually my question is.
Mm-hmm. A quick answer would be the importance of getting things published and increasing standards of what was expected of experimental research. Also, the experimentalists were often graduates of places where there were computers, so they had a desire to have their own lab, or when they were negotiating, they always wanted to they always mentioned things like, oh, I plan to have a computerized laboratory, or at least they were able to make use of a computer classroom that was eventually turned into more regular use for experiments. And eventually, when it was very cheap to buy 24 computers and get the space in an economics department, then they would get the laboratory itself. So I think the costs are part of the story, and the benefits of also of running those types of experiments in terms of publication success, and also the raising standards of types of research, but also I think that actually that's those two things that I wanted to say in terms of your question.
Beatrice?
Yes, I have a comment for later and a question for now. My comment for later is I'm not fully convinced by one interesting aspect in the paper is treating the materiality of computers in the spatial arrangement, but you seem to ascribe so much to the existence of the computer. I would have also dealt with the problem the other way. I'm not convinced that the computer determines spatial arrangement regarding, for instance, communication and information flows. And I would have studied how before the computer arrangement were made when it was like message and pen and pens on sheets and that were collected whatsoever, and whether, I mean, some arrangement that were decided in that era for information flow process sort of carried on, and how long and when it changes, because it would be interesting. I mean, if really you want to say that the computer changed so much things, that would be a nice evidence. And my question for now is regarding a conclusion that the people were really happy at some point with the computer. In the paper, you say like experimentalists were really happy because they say that would allow them to be more into smart markets. And I find it interesting because I find it a bit paradoxical, because one thing that it did not allow them to do is getting closer to real market operation. Because real market operation at that time was super messy. Even in financial market was communication breaking down. There was no way that instruction were delivered fast, or that everyone saw the same or whatever. And you insist that instruction are seen and delivered at the same time, and that people see the same thing at the same time, whatever. And so the conclusion is basically people were happy because computer were allowing them to bring their experiment closer to theoretical market, not real market. And do theoretical market that theories say delivered efficient outcome. And given all of the flag that experimentalists were taking at that time for not being realistic enough, I think this is a very interesting conclusion. If you agree that you can read it that way, that's a very interesting conclusion.
If you want to answer, yeah.
Sure. Yes, that's a very good suggestion to contrast the spatial arrangement and other sort of ways how experimentalists did pen and paper experiments before adopting and after adopting computerized technology to see really the impact of computers. But I would a bit disagree that computers did not affect, but perhaps I didn't understand your comment completely, that they did not affect the way how things were arranged in the space of the classroom or the lab itself. The very type of, like, the size of the computer screen, or where the computer screen is.
I was thinking of, you have a lot of pictures with how much walls you have to put in people, and how they should be located, and sound and stuff like that. And I would say, well, there must be a path dependency that doesn't depend on the computer, or if it does, maybe there has been change in that kind of thing.
Cool, thanks. I'll think about that.
There is a question now by Laetitia.
So I wanted to maybe emphasize that point about the prehistory. I think one aspect of it is just to look at it at all, or to stress it more in your paper, this prehistory. I found this intervention by Joan Aga and also Christiane van Oertzen, and I think I quote them also in my paper, really helpful, who say, and that's mainly Joan Aga, who said that computerization has only been attempted in settings where methods and material practices and technologies capable of the computational task at hand were already in place beforehand. And I think that's a really good thing to think about, because one is so, it's so easy to say, well, it has all been the computer, and tell this tale of technologies forward much. The second question is, you stressed that the computer technology played an important role in advancing the proliferation of economic laboratories in the 1980s and 1990s, and that these laboratories in turn played a crucial role in the experimental turn. And now I was wondering, would you say that the two laboratories with their distinct technologies for connecting computers, that they had different implications for the proliferation, not only of economic laboratories, but also for the experimental turn more broadly? Yeah, that's it. Thanks.
It's a rather deep question. Yes, they had impact on the proliferation of the type of computerized laboratories. There were not many Plato labs. There were a handful of them across the United States. There was one in Illinois, where I was a student of Vernon Smith, and who had the benefits of being in place where the Plato was born or was being used, and he used it until the early 2000s. But that was the last one to use. And the impact sort of to some extent followed the lines of students of Vernon Smith or visitors of Arizona who had experience with Plato and had some dipped their toes into tutoring programming language, and were able to make use of the local resources at the universities which had access to Plato to decrease the costs or offset the costs in various ways. But the impact of the computer technology, on a software level, I think the software level is far more interesting than the hardware level, because both groups try to generate or create various software packages that were sent around in floppy disks via mail to other research groups or starting experimentalists with instructions how to set them up on a computer. And since PCs were far more available than Plato terminals, then people were more naturally inclined to use PCs. And the availability of software or software packages was quite important in the uptake of experimental computerized research. So this sharing, this communal sharing, and this willingness to lower the barriers of entry to this type of research was very important in this rapid growth of labs.
Thank you. So if we don't have other question on this paper in particular, we could know, oh, okay, Marcel has one. Yeah,
I just want to follow up on the on your answer, Andre, about you mentioned well, it encouraged the publication kind of thing. It increases the or it made it easier to publish. I'm very doubtful about that argument. Empirical research, which also the other papers show, and experimental research is also empirical research, is very time consuming, because you not only have to deal with the data itself, but also with gathering and setting up the instrumentation, dealing with all the problems, actually the the main part of your story is very much about all the problems they were facing. So if you want to have a quick publication or you want to finish your dissertation quite soon, I wouldn't advise students to go enter the empirical research by doing the theoretical ones. So it still doesn't explain to me why you think that some contributed to the.
I think there is a bit of misunderstanding. I didn't say it was, or at least I didn't mean to say that it was easier to publish, but rather the standards of publishing experimental research grew in time, and having far better experimental control by using computers or computerized experiments became the norm. Of course, you could do pen and paper experiments for various settings which the control is sufficient, but the overall standards increased, also requiring far more observations, far more subjects participating, and using computers made us far more far less time consuming. So these increased communal standards for publishing forced people to adopt computers as well. Okay. Yeah. And these days, when a PhD student is struggling, often the advice is you should do at least an experiment, because that's manageable to get at least one thesis chapter. It will not be published, but it will get you a chapter sort of testing whatever you prepared in a theoretical chapter. So I would disagree with what you said, that empirical research will be not helping towards a dissertation.
Yeah, if I may clear, otherwise just stop me. But I would still like to challenge you, because it is about the timeline. The increase of laboratories is just before it became the standard. And so, so what you say about what's happening now, you are fully right. I agree with you. But if you look at, you showed us the graph in the beginning, and then you say, well, you're encircled that period you would like to address, where you really had an enormous increase in labs. That was before the kind of publication standard, and you have to do at least one experiment, etc., is after that period, I would say. That is something that only started in the 1990s. Mm. So this, you're talking about a period before it became standard, but it doesn't explain why this increase happened. I just want to challenge you on this.
So I just want to say that we can continue the conversation after the time, because then I will have the control of the Zoom room. So feel free to answer now, and then we could also have a more general conversation for those who want to stay in the seminar. Feel free to answer the challenge. That was my...
I would rather disagree with your claim about that the standards only increased from the mid-1990s or later. The publications, when you look at them in the first half of 1990s, in the top journals, all of them were already well, not all of them, but most of them. I think the most notable exception, I think, would be gift exchange experiments, where or the ultimatum game experiments, which some of them were done by pen and paper without computers. But most of the market experiments, which were very trendy in the late 80s, early 1990s, were all computerized. And looking at the trends at that time, the type of experiments that were being published would require using computers.
Okay, the challenge is still here, but maybe we could go to the general discussion. So I have one very short comment, but I think we could start by, I don't know, Beatrice, I know you had some comment on the whole session. We could start by this and then see how the discussion goes.
No, I think I met them in the several, okay. And I repeated the distinction between computing and computerization and the materiality and the politics of all this. So
okay, cool. I just have a point, actually. I'd like to hear all of you, but I also think we need to not be too long for everyone's brain. I'm just wondering about the comparison between the effect of computerization between different sector of economics, sorry, like micro and macro, for example, but also fields. And I wonder if you think that there is, of course, some field where this became more necessary, more substantial than others, and how we can quantify this sort of reliance of this new technology, and if the timeline is the same, the timeline between how it impacts some field and others. Yeah, that's my question I have, which is not very clear. Do you have any thought about that, or anything you want to say? And of course, feel free to go if you have things to do, because this is the regular end of the session. So don't worry, don't apologize, just go if you have to. And those who want to stay, of course, can stay. Not for long, basically. Yes, Marcel?
Yeah, just it is not actually, sorry, you're not really answering the point you raised, but I also have to leave. But I would like to say something to the three presenters, if that's okay.
Mm-hmm. Yeah, of course.
So all three of you very much, I think we would like to thank you very much for your all three wonderful papers. I think we did an excellent job at this ASSA session, and I'm really looking forward to the upcoming workshop, which will come somewhere, I don't know, after COVID or whatever going to happen. So I really hope to see you in person. And I think all the questions and the things you address are quite interesting and really up to the project, and actually starting to think about the role of computerization on economics as a science. And you all three did a wonderful job in that respect. So I would like to thank you for this. Even though I sound somehow a little bit critical, it doesn't, it's just that I hope that you use this kind of questions I have just for yeah, well, to think also about them. So thank you. Sorry, Cleo, that I
no, that's perfect. And I think if there is no other remark, I just want to join Marcel in thanking the participant. And yeah.
Well, thank you for organizing this session, Cleo, and thanks Marcel and Beatrice, who has already left. It's my baby. For your great questions and comments. And of course, Cleo, the thing you raised in the end now is a very important thing to think about. If the different sections of economics and maybe specific timelines, I don't have anything to say about that now, but I think it will be an important question also for maybe the entire special issue.
Yeah.
Laetitia, okay. I also one small question to you. Cleo just mentioned that you have finished your dissertation. Is that right? And yeah. Will it get a publication, or will it become a publication, or what's your plan with your dissertation?
Yes, I plan to publish it, of course, and just didn't find the time to write a book proposal yet, but
okay,
we'll do so. Yeah.
Would you mind? I don't know what the habits are at Humboldt, but is that something you can send around your dissertation, or is that something you cannot do with an Humboldt dissertation?
You mean send it to you, or?
Yes.
Yeah.
Is it possible to send a copy?
Yes, I could send it to you. Yeah, I haven't published it with the university so far because I thought, well, let's see what editors say and so on. But yeah, send it to you.
Yeah, I just keep it for my own. So I won't distribute it. I keep it just as a personal copy. But I would love to see the end result.
Yeah, I'd send it to you. Thanks.
Okay, thank you.
Does anyone wants to add anything, André? Or
Yeah, yes. Marcel, Beatrice, well, Beatrice is not here, but Cleo, if you have any written comments for improving the papers, then please share them.
Yeah.
It would be really helpful in updating the paper before the actual workshop, hopefully in person. That'd be great.
Okay. Yes, Pang.
I just want to apologize for my time control. So, but
No.
it's a really good session. So I'm really looking forward to a workshop if that happens, whether it's online or in person. Thanks for organizing.
Okay, so big thank you to everyone. Let's go back to our normal life. See you for the workshop, hopefully, and all the best for everything. So I'm going to end the meeting now.
Thank you.
So
Bye-bye.
bye. Thank you.
Thanks a
See
lot.
you.
Bye. Take care.
Bye.